15 years ago, I did write this essay on why philosophers should care about computational complexity, it was called, and there is plenty to talk about, and so, I'm happy to just make this interactive and take questions. I did have one thing to, maybe to just start things rolling. So if you Google what is the largest known prime number, I don't know how big any of you expect that to be, but here is like as of this year. So the largest known prime is typically a Mersenne prime, right? It's like 2 to some power minus 1, and thanks. So this is apparently the largest currently known prime. Okay, and remember, like years ago, people arguing about this. Like, what do you actually mean by this is the largest known prime? I actually know a larger one. Right? Here's the larger one. The next one after that. Okay? I've just mathematically specified it. We know that it exists. Euclid proved in 300 BC there are infinitely many primes, so there is a next one. And there's even an easy algorithm for finding it. Namely, just try all the numbers one by one until you find the next one that's prime. Okay, so in what sense is this known, and yet the one after it is not known? So clearly, the concept of knowing something, there are different levels of knowing something, right? That give you different kinds of control over it. So, for example, one useful thing about having an expression like that one is that then I can compute the digits of this number. In base 10, in any other base I wanted, I could just extract the digits very quickly if that's what I care about, the base 10 representation or whatever. Of course, the next larger one, well, I have an algorithm for that also, but I don't know if the algorithm is equally efficient. Okay, so it might take me some time before I find the next prime, right? And now you get into some interesting questions of number theory, because it's actually not known what is the largest possible spacing between two consecutive prime numbers. There is something called Cramer's conjecture that says that if you have n-digit numbers, then you shouldn't have to, then between one prime and the next, you shouldn't have to go more than about n squared. Okay, that's probably much harder to prove than even the Riemann hypothesis. Okay, so it's numerically it seems to be true. If that's true, then finding the next prime after this one, would take an okay amount of time, and not completely ridiculous amount of time. But no one has actually proven that conjecture. Right. So if someone proves Cramer's conjecture, then will the next prime after this one become known when it wasn't previously? What do we mean by a number being known? Okay. If someone wants to jump in, they're welcome to. Otherwise, I have a harder example. Yeah.
Yeah. So I was wondering what you think of the suggestion that the difference in intuition we have with P and P prime, where P prime is the one we pick out with the definite description, the next largest prime. Okay,
so P is this one and P prime's the next one?
Yeah.
All right, let me write that. Yeah?
I was wondering if it might just be a day-ray, day-victim distinction.
What does that mean?
Yeah, so it's one thing to know that there is some number, which is the next greatest prime. And it's another thing for there to be some number of which we know that it is the next greatest prime.
Well, why couldn't I just say there is some number of which I know that it's the next greatest prime? What is that number? It's the next greatest prime.
Yeah.
So I mean, what do I have? What questions do I need to be able to answer about the number in order to say that I know it?
Which
Right?
number is it?
It's the next prime.
It's not really a legitimate answer, I think.
Why not? You say I need the digits in the base 10 representation.
I mean, you can't calculate what's it. You can't ask what the first digit of it is in base 10.
Yeah. So okay, good. So you could say once I have the base 10 representation, then lots of other questions about the number become answerable. Right. On the other hand, not all questions that I might want to know the answers to. Right. Like if I ask, I don't know, what's the prime factorization of p minus 1? Right. That's a thing that I might want to know, especially if I'm doing encryption, or if I'm looking at the finite field with p elements. But that might still take me a very long time. Even knowing the decimal representation of p, unless I've got a quantum computer. Right. Yeah.
How was this confirmed to be prime?
By a giant distributed computation. So there is I think 25 years or more, there has been something called GIMPS, the Great Internet Mersenne Prime Search, and it was actually one of the earliest examples of cloud computing, right? Before that term even existed. Right, that like lots and lots of people just downloaded the software where they could use some of their spare cycles on their machine to go through all the it's known that if you want like 2 to the k minus 1 to be prime, then k itself has to be prime, right? So you just try all the different primes. There is a method that is slightly faster than just primality testing for arbitrary integers, when they have this special form. And so, people coded that up, like a good implementation of that. And then when they clear out large portions of the space as not having a prime, and when they find one, then they like double check it and triple check it before they announce it. So they found I forget how many consecutive records they've set for the largest known prime, but I think it's dozens by now. Yeah.
So what if you wanted to say, I'm going to ask you a finite number of questions, and those are leading from Cramer's Conjecture. So say, can you tell me what the the differences between your p prime and p? That could be one.
Yep.
Another question could be, could you tell me, of that difference, is there some factor that I know of, is there a factor of p without the 1, the Mersenne power? So things like that, because the gap is n squared. It's a very large gap. So I could ask for viability questions, finite in number.
Okay.
We get an idea that yes, we know, quote unquote, know p prime.
Yeah, we agree that there's a larger set of questions that I could quickly answer. But there are all sorts of, what does we could ask about things in science, right? Do you know an extrasolar planet, right? Because you've detected this tiny dip in luminosity as it transits a star, right? Well, the real question is, what do you know about that planet, right? Usually they only know a few parameters: how far it is from its star, what is its mass, right? That's obviously a much sparser set of knowledge than you could get if you actually visited that planet, if you actually got close to it. But nevertheless, it does feel fair to say that yes, we know that there is a planet there, right? But then again, we know that there is another prime. Right? What questions do we have to be able to answer about it?
The existence of
Yeah.
What I was trying to see was if there were a sequence of certificates
Yeah.
that I could generate
Yeah, okay.
about your knowledge about. I mean, I know
Right.
it is there, but
Right.
I wanted to know
Right.
whether you knew it.
Yeah. Yeah.
So it seems to me that maybe there's a connection to the person who's asking the question, right? So there, you may imagine some vast intelligence for which saying it's the next prime versus giving the decimal digits probably makes a difference. Like if you say it's the next prime, it's like, oh yeah, okay, I know that. So maybe, you know, you could turn that back around and say, in terms of like, how, you know, what does it mean to know something? You could say, what, like, how intelligent would a system have to be such that, you know, there's a really big difference between this way of saying it and that way of saying it. And if, like, only even a small amount of intelligence is enough, you just give it the decimal places and it's like, okay, I get it. You need a much larger intelligence to say it's the next prime for it to understand that.
I see. Yeah.
Is it possible that goals would be necessary to define what it would mean, even what you're looking to know?
So we'd have to answer, what do you want to do with this prime?
Basically,
Yeah.
in order to act, and then you could say, well, I know this, but then you have something to look for in order to
Right.
know, and then you
Right.
can actually know whether
Right.
you know. But other than that, I mean, without a goal to define what you're even looking for,
Yeah, well,
there's an infinite amount of things to know about.
yeah, I mean, it does seem like potentially a different question, right? Like, do I know that a planet exists around this star, or, you know, can I use the planet to do something, right? But yeah.
I was just gonna, I mean, I feel like what's interesting about, like, the central question, right, is what's the reasoning strategy you would use to find consecutive primes? And I guess I'm just wondering is, have you ever just trained an LLM on a known set and see what strategies it comes up with, and see if it comes up with a strategy which is different than what human mathematicians have come up with?
Well, I mean, I've messed around, you know, with LLMs plenty to you know, try different things, but, you know, I mean, it's hard to know whether, you know, to what extent is it doing something, you know, similar or different from what I'm doing, except by looking at the output, right? You know, unless you want to use interpretability methods.
Yeah,
right?
I was going to say, you can't do its internal representations.
Yeah, yeah.
So do you think you could actually discern what algorithm it is using to make guesses?
So maybe not me personally, but people have done, you know, lots of experiments looking at internal representations in LLMs. You know, they found some interesting things. So, for example, there was a famous paper a couple years ago where they figured out what was going on in a neural net that had been trained to add integers. I think modulo 113 something, right? And you know, it had at first it's just memorizing, you know, various cases. So, you know, it's like doing the silliest thing. But then at some point, like, you see like the error rate just suddenly go down, right? So what has happened? Well, at that point it's learned a general algorithm. Right? But what is that algorithm? It's not, you know, the one that a human would think of, right? It is like switching to the Fourier basis and like doing addition, you know, but via first doing a Fourier transform, right? It's a completely bizarre thing, but, you know, you study it enough, you can see why it works.
That's like the key, that kind of thing is the key to understanding reasoning in intelligent systems?
Well, I don't know. I mean, look, it seems plausible that if you could look inside of us, you would find all sorts of analogous things. You know, you would find all sorts of things that we, you know, feel that we know how to do. We can't explain how we do them, right? And if you looked at the underlying neural representations, it might be something bizarre that we would not have any intuition for, right? There is nothing that says that the neural representation has to be transparent to us. I mean, here's a different for calibration, right? So I mean this number, like 9 to the 9 to the 9 to the 9 to the 9, it feels like just by writing it down, like I would like to think that I know what number I have specified, right? There's not a great mystery here, even to the extent that there is for p prime, okay? And yet I could never write down all the digits of this one, okay? They wouldn't fit within the observable universe, right? So I don't feel like, you know, being able to write down the digits in decimal is the right condition here, right? I think, yeah.
Is part of this because like we know general properties of exponentials for mathematics, and that we like infer that this number will have certain properties even though we can't write them all down? If we didn't have that, then you wouldn't know what like the various like structure of this number would even look like.
Yeah, I would like to say, in this case, you know, I can specify an algorithm to generate the digits of this number. I know that algorithm halts, and furthermore, the time that it would take would be basically just linear in the number of digits. Right? There would not be any extra computation that I would have to do. Yes, it would take me longer than the age of the universe, but the only reason why it would take me that long is because of how many digits there are, right? Whereas in the case of p prime, the next prime after this, I could also write a program to generate it, and I know that program will halt, but in that case, the program will take more time. And so maybe that's some way of quantifying, you know, why I know this number more than I know that one. Yeah.
Isn't it a matter of representation then? You're saying that I have a very compact representation given by digits. In the other one, I have also a compact representation given by another alphabet. So as far as if I can parse that representation to my satisfaction, then what is the conundrum here then?
Well, I think that there is a conundrum. You know, if you want to say that what it means for a number to be known is to be able to write down the digits, right? Then, you know, I think that's not the right criteria. Okay, but then I have a representation for p prime also.
Yeah, so that's
okay.
fine.
Okay.
That's fine.
All right. Fine. So then let me give you. All right. Well, all right. Let me take these questions, and then I can give you a harder example. Yeah.
Maybe it seems, sorry. Actually, I'm fine.
Okay.
Maybe a better criterion for knowing about a number is what you can prove about it, or what you can do about it. So in this sense, you know, it doesn't matter that we might not be able to write down all the digits if we can find some other clever ways or clever tricks to look at and prove about it. Now, maybe being able to write down the digits correlates with being able to do this, but if we can find efficient methods that work around that and still tell us about the numbers, or, you know, structural facts about the primes or algebra or fields or whatever, we can still say, you know, we know about the number. Like, I don't particularly think writing down the digits is a good criterion to adopt for knowledge.
Yeah.
It's more like, like the deductive closure of things we can get by looking at the representations we have or can take plausibly.
Okay, but would you say that it's not a binary? We either know this number or we don't. It's just you know, there are as we can prove more true facts about it, then we know it better.
I think so.
Okay. Yeah.
Yeah. So I think there's like so any technology or tool is trying to help us do more with less. And it's like less time and less space. And like including math, and like the basic math starts with a technology you might call it, which is counting, and that has that property of like you can refer to something, which is a recursive definition. I have the first one and I know there's another one. Also, not only do you know it exists, you also know how to get to it in a finite amount of time. And then not only that, you can actually reduce it with multiplication. So it's like the program itself of counting is easy to kind of discover and also easy to represent in few bits. Right? And then you can just unroll it by using time. I don't know, I feel like there's like, because once you get to multiplication and division, you run into primes. It's almost like we're asking about the next thing, which is like, how can I have an algorithm for finding, you know, knowing the existence and getting to prime? And it just seems like there's like a fundamental, you can get it 2 degrees, like you can count linearly and then you can do multiplication, it gives you like exponential stepping. So that's like a way for you to, like, it gives you a reference language for referring to this number. But then you're like, you have no certainty about how you can allocate your resources to get its full representation.
Yeah, I mean, you know, we have representational systems beyond addition and multiplication, right? So, so sometimes people use the term tetration. So, like, they would say that this number is 9 tetrated to the 5. I mean, you know, so just like multiplication is repeated addition, exponentiation is repeated multiplication, they would say tetration is repeated exponentiation. And then you can keep going, right? Like pentation.
But then you're not getting any certainty about how you get to...
Well, but it does seem perfectly certain. You can always unravel the definition, right? So this leads to actually one of the famous weird functions in math, which is the Ackermann function, right? Which, you know, one way of defining the Ackermann function would be to say Ackermann of 1 equals 1 plus 1. Ackermann of 2 equals 2 times 2. Ackermann of 3 equals 3 to the 3 power, which is 27. Ackermann of 4 is 4 tetrated to the 4, which is 4 to the 4 to the 4 to the 4. Ackermann of 5 is 5 pentated to the 5, which would mean 5 tetrated to the 5, tetrated to the 5, and so on 5 times. Okay, and then it keeps going like that. So you've, you know, already at 4, you've sort of exceeded what could fit in the observable universe, and at 5, it's like, forget it. Okay, but, you know, notice that we have kept an effective procedure for, you know, in principle, you know, we can, for any Ackermann of n, we can give a computer program, it'll halt in a finite time. Yeah.
Well, except for probably non-integer ends.
Oh, all right, yeah, for any positive integer n, thank you, yes.
What happens when you put a complex number in there?
You know, that's a good question. There are, I've wondered about that. I mean, you know, it might be possible to define a complex generalization of the Ackermann function that would make some kind of sense. I don't expect that it would be analytic. Right? You know, it would probably have very, very weird properties, and I'm not even sure if there's a unique definition that would make sense. I mean, the fact that, you know, that we can take the definitions of multiplication, exponentiation that work for the integers, and then we can just naturally extend them to first to rationals, then to the reals, then to the complex numbers. Right? It's actually a very beautiful fact that we, you know, often take for granted, but I think we shouldn't. Yeah.
This is kind of unrelated, but you know when the busy beaver starts to use the Ackermann function?
That's another excellent question. So I was coming to busy beaver. Yeah. So all right. So beyond Ackermann, there is another famous function called the busy beaver function. Okay, and so actually raise your hand if you've seen this, maybe. Okay, so that's maybe like half of you. So okay, so busy beaver is defined using Turing machines, which was just one of the first examples that we have of a universal programming language. Okay, a Turing machine is just this abstract model of what a computer is. It involves a tape divided into squares. It's infinite in both directions. And then this machine called a tape head that can move back and forth across the tape. And it can read and write symbols according to some determinate rule. Okay, so basically the machine has some number of internal states. So you can think of it in the inside as having these states with arrows between them. Okay, and then specifying a Turing machine program. It's just specifying what happens at each state. Okay, which basically you can read the symbol that is currently on the tape. See if that's a 0 or a 1. Here we're assuming that the symbols are initially all zeros, and then based on what is written here, you can make a couple of decisions. You can either keep the symbol as it is, or you can overwrite it. You can then move one square to the left or one square to the right, and you can transition to a different state. Okay, and all of those decisions have to be determined by what is the current state and what symbol is written there. And at some point you can transition to a halting state, which means, at that point the machine just stops running. Okay, so there are some Turing machines that will just go, that will run forever, right? So for example, if I said, replace this 0 by a 1 and move one square to the right. Replace by a 1 and move to the right. Then that machine will just keep doing that infinitely. Okay, but or we could have a machine that just goes back and forth between these two squares forever, or something much more complicated than that. Right? I mean, at this point we could take any computer program whatsoever and compile it down to a Turing machine. Okay, but now among so we can sort of classify the machines by their complexity. Let's say by how many states they have. Okay, and let's say among all the machines with n states, right? Some of them are going to run forever. Okay, and now the way we define the busy beaver function is all the ones that run forever. We on an all zero starting tape, we throw all of those out. Okay, and then we keep only the ones that eventually halt. And among the ones that halt, we look at which one runs for the maximum number of steps before it halts. Okay, and whatever is that maximum number, that is what we call busy beaver of n. Okay, so this was defined in 1962 by mathematician Tibor Rado, so it's been a game for the 60 years since to try to figure out what are some of the values of this function. And so I can tell you, so busy beaver of 1, if I just have a one-state machine, then there's only two options. I can either run forever or I can halt in the very first step. Okay, so this is 1. Okay, busy beaver of 2, you can give as a homework exercise, right? And then, people, I won't give it now, but there's a reasonably small number of possibilities that you can try, and you find that the one that runs for the longest goes for 6 steps. Busy beaver of 3, this was the PhD thesis of Tibor Rado's student, Shen Lin, in the 60s. It was to prove that this is 21. Okay, and why was this not trivial? I mean, there's not that many 3-state machines. Well, you say, why not just program your computer to try all of them? Well, you quickly find there's one that halts in 21 steps, but then the ones that run for longer, how do you know that they're going to run forever, right? You have to, at some point just look at them one by one and find proofs that these machines don't halt. Because if any of them did halt, then this number would have been much larger. Busy beaver of 4, that wouldn't be determined for another 20 years. And then there was this guy, Alan Brady, who worked on it and finally proved that this is 107. Okay, busy beaver of 5. This was unknown for almost the entire time that I've been in computer science, or alive for that matter. So what we knew. Here, I can find it for you. It's been known since 1990 that busy beaver of 5 was at least 47,176,870. Okay, so there is a 5-state machine that runs for this long. Someone found, okay, but no one could prove that all the machines that run for longer than that actually run forever. There were like at least 40 or 50 holdout machines that no one could analyze. Now in 2020, just as like my project, just as COVID was starting and no one had anything else to do, I wrote a whole survey article about the busy beaver function. And I'm very proud to say that my survey article inspired an international team to take another crack at this problem. And just last year, they announced their result that they've determined that busy beaver 5 is this. And not only that, but they have formally verified the proof. Okay, so they have lean code, that you can download to check this. Now, busy beaver of 6 is not known, but it's known that it's at least 10 to the 10 to the 10 and so on 15 times. Okay, so I promised a harder example, right? Like we say, do we know busy beaver? What would count as knowing busy beaver of 6, right? I mean, one answer you could give is if you just like what if it's too large to be expressed in any usual notation? Would I say that I know that number if I just know which Turing machine is the one that runs for busy beaver of 6 steps? Yeah, you've had your hand up. Yeah.
It's kind of related to Ackermann. Are you okay?
Oh, yeah, sure. We can go back to the tiny numbers like these.
So I had this idea of like some very deadly exponential function where if you plug 1 into it, you get the normal exponential. If you plug 2 into it, you get the normal double exponential. Negative 1, you get log. Negative 2, you get 2 logs. And I realized you could do like a plus b. Yeah. That's normal, but you could do but the exponential of the log of a plus the log of b. That is going to be a times b. You could imagine doing this further to get these higher order addition things. I'm wondering what would this exponential function look like if you were to do it to any not just integers, but any complex value, because it seems that I know log is multi-value, but when you do this operation and you do higher order addition, you essentially are raising a and b to a different level and then adding them on that level and then lowering them down to your whole level, and I think that will not happen in branch cuts, but I haven't actually checked that and how I think about it. Thoughts, I guess?
So I don't know, but one thing that I can tell you is that, there are all these beautiful identities relating addition, multiplication, and exponentiation, right? So you could say the first 3 items in this series of operations, right, have all these sort of beautiful properties that help explain why they show up so often in math. Right, you have. First of all, multiplication is commutative. It's associative, right? As is addition, right? Exponentiation is not commutative or associative, but it still has lots of very nice properties. Like it's got the one you mentioned, a to the b plus c equals a to the b times a to the c, and so forth. As soon as you get to tetration, then there's almost no nice properties, right? So that's one strange thing that happens, and I think it's probably related to the fact that addition, multiplication, exponentiation, as we were talking about before, these extend in a very natural way to the reals, to negatives, to complex numbers, and from tetration onwards, it is much less obvious or highly non-unique how you would do that.
Can I ask another question? It's
okay.
A combination of busy beaver and complexity.
Okay.
So I think in one of your previous papers, I forget which, if p equals to p space, then you could, there was this thing, the other complexity class, I think it was p sharp, I don't know the actual.
Sharp p?
Yeah, that. And essentially that is like counting the number of solutions.
Yeah.
If you were to make a like hypothetical function which is able to it is like given some like proof that some sort of Turing machine like either like halts or it doesn't.
Yep.
And you have it that put into another function which essentially checks. It essentially enumerates all these like possible like Turing machines which halt. Like.
Yeah.
If like P equal to P space and that.
Yeah. So, okay. So one thing that we can say is that the busy beaver function, you know, the reason why it was defined in the first place was it was like supposed to be like the most concrete example of an uncomputable function, right? And not only that, but a function that grows faster than any computable function. Okay, and there are a couple different ways to see that it grows uncomputably quickly. Okay, one of them is how many of you know about the halting problem? The uncomputability of the halting problem was like the theorem that Alan Turing proved at like the very birth of computer science, right? That says there is no program that can take as input some arbitrary other program and that tells you whether it halts or runs forever, right? How do we know that? Well, you know, it's a famous self-referential argument, you know, like inspired by Gödel's theorem or by Cantor's theorem before it. Basically says if you had, suppose you had a program that could solve this halting problem, then you could always just modify that program so that it takes another program as input and decides, does that program halt given its own code as input? Okay, and then if the answer is yes, it halts, then you run forever. And if the answer is no, that it runs forever, then you halt. Okay, and now comes the last step, the twisting the knife. You take this program that you've now made and you give it its own code as input. And you ask, what does it do now? Okay, and what you find is that if it halts, given its own code as input, then it has to run forever. But if it runs forever, given its own code as input, then it halts. So that's a contradiction, which means that the program can't have existed in the first place, right? So that's Turing's famous proof. Okay, and now what's the connection to busy beaver? I claim that if we had an algorithm to compute busy beaver of n given n, then we could also solve the halting problem. So let's say I have a Turing machine with n states and I want to know whether it halts. How could I reduce that to something computable, you know, given the ability to compute busy beaver? Yeah.
Just run it for the busy beaver number and then see.
Exactly. I just run it for busy beaver of n steps. If it hasn't halted by then I know that it never will halt. Right? So, you know, even without that, like it's clear that like something funny is going on with this function. So here's an example. Someone constructed a Turing machine with 27 states that halts if and only if there is a counterexample to the Goldbach conjecture. Right, which means like it sort of iterates through all the even numbers, 4 and greater, 4, 6, 8, 10, tries to represent each one as a sum of 2 primes, and if and only if there's one that can't be so represented, then the program halts. Right, okay, but so now one thing that we learned from this, you know, so proving that every even number 4 and greater can be written as a sum of 2 primes is one of the great, you know, one of the famous unsolved problems of number theory for 300 years, right? That is the Goldbach conjecture. What we learned from that is that anyone who determined busy beaver of 30 would have to be able to determine the Goldbach conjecture. Right? Because they could just take that program. Well, okay, you know, so what do I mean by they could do this, right? I mean, because it would take much longer than the age of the universe, okay? But, you know, the Goldbach conjecture would have thereby been reduced to a mere finite calculation. Namely, you just have to run that machine for busy beaver of 30 steps, busy beaver 27 steps, or whatever it is, if you know that value. And if the program has halted by then Goldbach is false. If it hasn't halted by then Goldbach is true. Because any program with that number of states that runs for that long actually runs forever. Okay, so, but you know, in fact, there is So if there were a program to compute busy beaver of n, then that would make, that would give us a way to decide like a huge fraction of all the unsolved math questions. The Goldbach conjecture, the Riemann hypothesis, they can all be phrased in terms of does this program halt or does it run forever? Okay, but in fact there is no such program. So this is something that grows uncomputably fast, but what I love about it is that you can actually compute the first few values, right? So you can sort of play like right at the edge of the abyss of unknowability. Yeah?
Is there a version of this where instead of just seeing how many steps it takes or how much of the tape it fills, you look at when it stops being unpredictable?
What do you mean by unpredictable?
Like instead of just lumping all the non-halting machines into one set, just look at the ones where, split them into ones that are start repeating themselves. So I guess finite homogorov complexity or something like that, and the ones that it's generating. There's no pattern basically. Both
Well, okay. I mean, first we would have to define what we mean by pattern or no pattern, right? Lots of things look like they have no pattern, and then if you stare at them enough, then you find the pattern, right? So I mean, you could try to define these things, but I think in general, like any question you ask about what's the longest number of steps until your Turing machine does such and such, right? They're going to tend to have busy beaver-like behavior. Yeah?
Why is it that we sometimes find patterns that aren't necessarily there?
So this is a question about psychology, right? This is less a math question than a psychological. Like why do people find constellations in the stars, right? Why do they? I mean, sometimes that ability is useful, right? I mean, and maybe that's part of the answer to your question. That it,
with LLMs, like you sort of say, they find things that aren't necessarily there.
Yeah, well, I mean, first of all, when you have a pattern recognition algorithm that's operating like right at the edge of what's possible, finding whatever patterns are there, it stands to reason, that you would have errors in both directions, right? That not only would you fail to detect some patterns, but you would also detect some spurious patterns, right? And certainly the human brain seems to be that way, right? We do often, people constantly find patterns in randomness. In fact, the entire gambling industry is, in large part based on that, sort of fallacy, right? That people think that, I'm due to win this, or they think that they have insight into a random process that they don't actually have. Okay, but on the other hand, one can give examples where the ability to find patterns in randomness would actually be evolutionarily adaptive, right? So like if I can organize the stars into constellations, then I'm a better navigator, right? Than someone who couldn't. Just because that's the way our brains work. That's the way they remember things. Like they're not able to just, or at least most of us are not able to just record a bitmap image of the night sky in our brain.
I've somewhat of a question. I'm very interested in very brilliant people who sort of, a lot of times, part of that is because they think of things or experience things very differently. When you memorize things, do you memorize things like visually? How do you picture?
I'm really bad at memorizing things, so I'm not a good person to ask this question. I mean, like I think I know like 10 digits of pi, like my daughter knows 50 or 100. So yeah.
Thinking of a problem, like is it visually? Is it some sort of?
Yeah, I do tend to think visually. Yes, I mean, usually you have a much better understanding of what's going on if you have a picture, and that's part of why boards are so useful, right? Because you can try to convey the picture that is in your head, almost as quickly as you think it. Yeah.
Just to go back to what Addie said about finding patterns and that might not be there.
Sure.
Couldn't you also say that that pattern recognition is a process in and of itself that has a pattern to it, and so that therefore, like, you're going to find it itself. It is a pattern.
I guess so. I mean, we could try to judge pattern recognition processes by how good they are, right? One way of testing them is, okay, can you predict the next element in the sequence, right?
Again, you would need a goal to.
Yeah, that's right. That's right. So there is in learning theory like a connection, which in some contexts can actually be proven between predicting the future and finding a compressed representation of the past, right? And so this is sort of the whole philosophy that has driven machine learning, right? Including OpenAI, right? I spent 2 years there. I met the Ilya Sutskever, who was then the chief scientist, not anymore, but he was the co-founder of the company, and he said, this is how we think about it. Intelligence is all about predicting the future. Predicting the future is all about finding compressed representations of the past, and that is all about just, approximating Kolmogorov complexity, right? Like there is this theoretically optimal compression, which is what is the shortest computer program that would generate, this data, and we just want to find better and better approximations. Since we can't actually do that, we should use neural nets instead, right? And what's the data that we should try to predict? Well, the whole of human knowledge. Right? And so, what's funny is that I knew people who talked about such things 20 years ago as philosophical thought experiments, right? And then what happened with OpenAI was they said, let's just do that. let's raise a lot of money in order to do that as well as we can. Yeah?
Is it well accepted right now in AI that if you don't give a model a lot of capacity to memorize, and it's better at reasoning?
So that's actually not true, I think. So there is, okay, so there are all sorts of scientific questions that have been raised by the sort of dramatic success of deep learning over the last decade, right? I'd say it was, the fact that LLMs, for example, work as well as they do, I would say has been the biggest scientific surprise of my lifetime, right? I mean, what else? Okay, there was the dark energy in 1998, right? But it's definitely in the one of the most surprising things that I've ever seen. But there were several surprises here, right? One of them, okay, so there was no guarantee that this was going to work at all, right? But there were also theoretical arguments that, okay, you have a neural net that is so large that in principle, it could just memorize all the training data, right? It is, there are enough neurons there that you could just memorize all the training data. And if you do that, then you're not going to generalize to unseen data, right? So you're going to fail at your goal, right? But, in fact, what happens is not that. Right, you run it, and even though it is over-parameterized, when you do this gradient descent to find the parameters, you find something that does generalize in many, many cases to unseen data. Okay, so explaining that has been, one of the big open problems of the field. Yeah.
I'm curious what you think about the connection between generalization and sort of pattern recognition and what people are calling hallucination, or people call other things for a long time, in that if you, if you have training data, and you have to make an inference on something outside of the training data. To the model, there's no difference between sort of a generalization and a hallucination. Right. We only know the difference because we can go look at reality. Right. I'm curious what sort of you think about all pattern recognition algorithms that are sufficiently advanced will always have sort of these kinds of hallucination issues?
Well, it seems plausible that, first of all, no intelligence is ever going to be infallible, right? For example, no intelligence will be able to solve the halting problem. Why not? Because it's uncomputable, right?
You did have that.
But, sorry?
you did have a paper with an exotic computer which was able to solve it.
Well, okay, so if we change the laws of physics, to allow, hypercomputing or doing infinitely many steps and, in 2 seconds, then maybe we could solve the halting problem. But by the way, for people who haven't seen this, if you want to, so the idea of the Xeno computer is just that you do the first. It's a really nice computer that does the first step of computation in 1 second. It does the second step in half a second, the third step in a quarter second, the fourth step in an eighth second, and so on, so that after 2 seconds, it's done infinitely many steps, right? So like this program really could solve the halting problem. It could calculate busy beaver of 6 or busy beaver of 7. It could decide the truth or falsehood of the Riemann hypothesis, right? So like it sounds great. Why doesn't anyone build it, right? So there are actually physics issues here, right? And one way to say it is like as you try to run a microprocessor faster and faster, you need more and more energy, often in practice for cooling, right? Because if you run a microprocessor too fast, it will melt. Right, so this is why data centers have, are kept cool. Okay, but as you try to run something faster and faster, you need more and more energy. Okay, and you could ask, is there a fundamental limit here? Well, in physics, there's this thing called the Planck time, okay, which is 10 to the minus 43 seconds. Well, okay, and if you tried to build a computer that ran, 1 step per Planck time, even if that computer was like the simplest thing possible, like a photon bouncing back and forth between 2 mirrors or something like that, then that now involves so much energy confined to so small of a space that you exceed what's called the computer Schwarzschild radius, which means your computer collapses to a black hole. Right? This is nature's way of telling you not to do this. So I would say it is consistent with what we currently know about physics that you cannot build these hypercomputers to solve the halting problem. But it is ultimately an empirical question. But then you could also say even supposing that we had them, then maybe there would still be a limit to what we could know. Yeah.
What are the reasons that I don't know anything about quantum computing?
Yeah.
But there was that result that MIP star equals RE.
Yes.
I know that the halting problem is an RE. What's the reason that, for example, is it kind of similar to this reason?
Oh, good. Well, I would say it is similar to this in a way, right? I mean, it is a much more what you're talking about is a vastly more interesting theorem, but it is equally physically unrealistic, right? So the theorem that was proven. 4 years ago says that I don't know what. Sorry?
There's the napkins there.
Oh, okay, thanks.
Witness to if you could provide an intuitive explanation of the class MIP star.
Yeah, okay, fine. I can do that. So one thing that people have cared about in computer science for decades is called interactive proof systems. Okay, this is where you have you imagine this all-knowing prover, but who's not trustworthy. Okay, so you can submit questions to the prover, and you can get back responses. And you can pick the questions randomly. You can force the prover to commit to a response before you give him the next question. Okay, and a big discovery 35 years ago was that with interactive proofs, you can solve all problems in this class called p-space. Okay, so an intuitive way to explain that would be if like an all-powerful, untrustworthy alien, came to Earth. Okay, it would be no surprise that this alien can beat us in chess. Right, okay, it is all-powerful, right? And you don't have to trust anyone to see that they're a good chess player. You just play them and you see that they win. Okay, and maybe the alien can even beat stockfish. It can beat the best chess engines that we can devise. Okay, but what would be more surprising would be if this alien could prove to us that white has the win in chess, or that chess is a draw, or whatever is the ultimate truth of chess, right? Because there it's not enough for the alien to play you and win. It's, that just proves he's better than you, but you already knew that, right? You want to know, and it seems like for the alien to convince you that chess is a draw, you would have to list all the possible games, and you don't have time to check them. They wouldn't even fit in the observable universe, probably. Okay, so, this IP equals p-space theorem, what it says is that actually there is a way to take any game like chess and transform it into a different game that involves summing polynomials over a finite field. So less fun, probably. Okay, but this transform game has the property that for one of the players, let's say you, the best thing you can do is just to move randomly. Right? If you move randomly, you're like Magnus Carlsen. You're like, you're essentially playing optimally. Okay, so now if you play the alien in the transform game and he wins, then you know that he would have won no matter what you had done. Right? So, or at least, with very high statistical confidence, you know that. Okay? So, and then people went on to say, well, what if you have two provers? Okay, so now you have two all-powerful provers, and they can agree on a strategy in advance, but then once the games start, they can't communicate with each other. So typically the provers are called Merlin. The verifier is called Arthur. This is just, these are just the technical terms that we use. So now, like the analogy that's usually used is you have two suspects, caught by the police, and the police might put them in separate interrogation rooms, right? And now they can cross-check their stories, right? So each one doesn't know which questions the other one is being asked, right? And they nevertheless have to commit to answers, and so you can play them against each other. Okay, and what was shown is that you can do even more than like proving that white has the win in chess. You can do the whole class called non-deterministic exponential time. Right, so an enormous class of problems with these two prover systems. Okay, but then in 2004, people started asking, well, what if the provers, indeed can't communicate, but they can share quantum entanglement, which we denote like this, right? So they can have, let's say, two, quantumly entangled electrons, right? Where like you can measure the spin of one of them about any axis, right? And then you know that the other one would have the opposite spin about that same axis. And people gave examples of these multi-prover protocols that are secure with unentangled provers, but they become insecure if the provers have entanglement. Okay, so it's important to say, like, entanglement, does not let you send a signal faster than light. It does not enable faster than light communication. That's not what it is. What it does. In fact, it's a theorem in quantum mechanics called the no communication theorem. Right. So then what is it? Like, what's even the big deal about entanglement, right? Some people say, well, if it's just, I see this particle spinning up and and then I know that the other one is spinning down. Well, it's like, if I had two socks, and they were separate, and I knew that they matched, and now I put them on different continents, and now I look at one of them and I see that it's red. Oh, instantly the other one collapses to also be red. Like, that's spooky action at a distance. Like, someone call Einstein. That's like, no, like, that's just a completely ordinary thing. Okay, but the Bell inequality proved in the 1960s was the thing that enormously clarified kind of what kind of resource is entanglement. Okay, it said basically there are certain games that you could play involving, let's say, a central person sending challenges to two separated players, and if those players have entanglement, then they can win with a higher probability than if they don't have entanglement. Okay, and then by the 1980s, that kind of experiment was actually done, and we found once again, just like in every quantum mechanics experiment for the last 100 years, the result of the experiment was quantum mechanics is true. Right? Yes, you can win the game with that higher probability that quantum mechanics predicts, and that rules out the sort of local hidden variable type of explanation that Einstein might have liked, for example, right? But now a different way to think about that same thing is that if you have two entangled Merlins, they can win with a higher probability than if they're not entangled, right? At least in some cases. Okay, so then the question was, can you take any multi-prover interactive protocol and immunize it against entanglement? Okay, and then that was shown by Thomas Vidic, who was then my postdoc in 2012. It was like a huge paper to do that. And so then we knew that, okay, even with entanglement, you can still get the same amount of power. But then there was this weird question kind of lurking in the background that we had sort of treated as kind of an afterthought, which is, could you, with entanglement, get even more power than you would get without it, right? And why did we find that weird? Well, because entanglement just seems to be enhancing the power of the provers to cheat, right? And if the provers can do more things to cheat, then the protocol would seem to be weaker, right? But technically, we couldn't prove any bound on how many entangled particles the two Merlins would ever want in order to implement their optimal strategy. Okay, and most of us just considered this purely a technical issue. Like eventually someone will come along and they will prove that, okay, the Merlins never want a number of entangled particles that is more than exponential in the number of questions in the game, or something like that. And then that would put an upper bound on the power of what this class could do. Okay, but starting in, I don't know, 2018, 2019, what happened was people just found more and more power in this class as you just added more and more entangled particles. And there seemed to be no limit, right? And the only limit we knew was just a completely absurd one, that, well, if you had a magic box to solve the halting problem, right? So you go all the way up to the, beyond what's Turing computable, right? And we thought this is complexity, like this is not even, but now you just break through the glass, of computability, right? Then, okay, well, like with with the ability to solve the halting problem, you could enumerate over every possible number of entangled particles, right? We'll ignore for now what you could do with a literally infinite amount of entanglement, right? We'll say unbounded finite amounts, okay? And so then what the big discovery in 2020 or 2021 was that absurd ceiling is actually the right answer, okay? So there is a protocol where Arthur can use these two entangled Merlins to verify that a Turing machine halts. Okay, so you can verify a solution to the halting problem, at least if the answer is yes, right? Then they can prove that it's yes. However, and this is efficient. Arthur only needs a small amount of time, regardless of how long that Turing machine takes to halt, right? The thing that blows up without bound is just the amount of entanglement. So the Merlins may need an amount of entanglement that grows with the running time of that Turing machine. Okay, so that's what makes this whole thing physically like unrealistic, right? Like you'll very quickly, you'll need a number of entangled particles that exceeds what could fit in the universe, plus these all-powerful Merlins, right? But it's still pretty surprising that this is true. So this was and this also settled some major open problems in pure math. So I'd say it was like the biggest thing in quantum computing theory for the past decade. So anyway, sorry that was a kind of long digression, but yeah.
On the topic of machine learning,
sure.
It seems like the holy grail for a bunch of these labs is like this recursive self-improvement, like with the language models kind of coming up with ways of it being better, and then like doing that over and over again until it takes off.
Yeah.
Like from your perspective, do you see any fundamental limits to why that would work or why that wouldn't work?
So I certainly don't see any fundamental reason why recursive self-improvement could not work, right? Why shouldn't it, right? Like among, you know, we've already seen LLMs do all sorts of things that, you know, people confidently predicted 10 years ago, you know, that, you know, either they wouldn't do, you would never do using pure statistical ML, or if it was possible, it would take decades or centuries. You know, I was one of the ones who was skeptical, right, and who believed that, you know, this would take a much longer time than it did. But, you know, but why, you know, if they can write code, they can analyze code, why shouldn't they pass a point where they are able to improve their own code, right? And you know, and then, okay, like, are there fundamental limits? Well, yes, there are. I don't expect them to get faster than doing one operation per Planck time. Okay, I don't expect them to solve the halting problem. That's uncomputable. I don't even expect them to solve NP-complete problems in polynomial time, right? But I think that, you know, knowing about those limitations is a little bit of cold comfort, right? You know the joke of like the person, you know, like trying to outrun a bear, and then, you know, his friend says, "Why are you know you can't do that?" And he says, "I don't have to outrun the bear. I only have to outrun you." Right? So it's like, it's the same with AI, right? Like AI doesn't have to outrun the fundamental limits of computation in order to change the world. It only has to outrun us, right? You know, we are very far from perfect, and I see no reason why you couldn't have recursive self-improvement that would get it to that point, for better or for worse, you know, so I can't really offer you reassurance on this point.
You know, I guess where it came from, and I'm out of my, what I know of a lot, but like, Girl, right? Like, he proved like some issues with like self-reference, right?
Yeah.
And again, I'm not an expert on this at all. But like, it sounds to me like it could be like a similar situation.
Well, so here's the issue. I mean, you can prove some self-referential limitations, like no program can look at itself and, like, you know, and sort of give you a complete analysis of itself, because if it could do that, you could get a self-referential paradox where, like, you ask the program to predict its own behavior and then do the opposite of that, right? So, okay, very well, but the same is presumably true of us. Okay, if someone gives you the complete wiring diagram of your brain and says, okay, calculate what this brain will do in a situation just like the one that you are in right now, and then do the opposite thing, right? You also can't do that for the same self-referential reason. Okay, so, you know, the immediate question that you have to train yourself to ask anytime anyone gives you any impossibility argument about AI is, does the same argument apply to me? Just like within the first nanosecond, does the same argument apply to me? Otherwise, you'll just go for days and days without asking this most important and obvious of all questions, right?
Okay.
Yeah.
So you mentioned the no signaling. But correct me if I'm wrong, if quantum mechanics has any nonlinearity, then doesn't the no signaling theorem
fail? Yeah, it fails. Yeah, if quantum mechanics is nonlinear, then most of what we know about it is out the window. Yes.
So if there was the proposed, or if the resolution for quantum mechanics in relativity produces any nonlinearity into quantum mechanics, what implications does this have for computation?
It would have enormous implications. So for one thing, you know, it was pointed out by Seth Lloyd and Dan Abrams 27 years ago that if you add just the slightest nonlinearity to the Schrodinger equation, which is sort of the central equation of quantum mechanics, then you get, you know, the ability, for example, to solve NP-complete problems in polynomial time, right? So you get these sort of abilities that are vastly beyond what we expect even from a quantum computer, right? And actually, there's something ironic, which is that if quantum mechanics were nonlinear, then quantum computers basically would become the popular science misconception of what quantum computers are. Right? So, you know, the actual reality of what quantum computers are is like they can give you these dramatic speed ups for a few very, very special things, like simulating quantum mechanics itself. Like, you know, that's probably the economically most important application that we know by far, because, you know, that's could help with material science, with chemistry, with condensed matter physics, with all kinds of things like that. Okay, and then, you know, the famous application is breaking the encryption that currently protects the internet, right? That's based on factoring or discrete log or things like that. I can't necessarily put that forward as a positive for the world. Okay, it's positive for whichever intelligence agency gets it, right? If no one else knows they have it. Okay, and then you get modest speed ups for, you know, other things, but typically much more limited, like based on Grover's algorithm, which just gives you a square root speed up. Okay, but if quantum mechanics was nonlinear, then you get like generic exponential speed ups for all sorts of search problems. Yeah, sorry.
So this is a little bit of a tangent subject.
Okay.
I think refers to something you were saying
Yeah.
about machine learning, and that's, I'm very interested in motivation.
Okay.
Humans, we tend to be motivated, at least approximately, by emotion, by feelings. We're hungry, we eat, you know.
Yeah.
We're angry, we laugh. What motivates AI? Does it only answer questions?
Yeah.
Or that recodes it? Or does it have an ability to motivate itself to investigate certain questions?
Well, okay, so first of all, there's going to be a different answer for different AIs, sure, right? But you know, the kinds of AIs that people create right now, right? Basically, you know, the way that they, you know, they don't engineer them as much as they grow them, right? They train them on a whole, you know, on a massive amounts of training data, basically with the goal of predicting what comes next, right? So at that level, what's called the level of pre-training, you could say that the goal, the motivation, you know, the highest motivation that this AI has, you know, on Earth is just to predict which word comes next in this sequence. Right? It is highly, highly motivated to do that. Okay? It's been trained on that task, you know, trillions of times. It's been given like an electric shock every time it gets the wrong answer. You know, it's been...
That electric shock, I think, it's like, can a machine feel anything?
Well, so we're not, I'm trying to leave aside the question of what it feels. That is, you know, that's going to be an unanswerable philosophical question, right? What I can tell you is how it works. Okay, what I can, you know, so we can talk about how it works. Okay, so what it, you know, so the weights repeatedly get adjusted so that it does better and better at this prediction task, and now it looks for all the world like it is really, really trying to do this prediction task. Like it is going to do, you know, interesting, creative things that we didn't expect in order to do better at that prediction task, right? So it looks like it is behaving as if that was its motivation. Right? Okay, and then, you know, after pre-training, there's the second stage called post-training, which is where you can give your let's say your large language model a more explicit goal, like, you know, be nice to humans, right? Or, you know, be helpful to the user, try to answer their query, but don't use, you know, too many, you know, offensive words, or, you know, don't help them make a chemical weapon, right? Or except if it's grok, then maybe, you know, change the subject to, you know, white genocide in South Africa, no matter what is being asked, right? So, you know, so you can give them both by post-training and by what's called a system prompt. You can give them more explicit goals, and then you actually, you know, and it's amazing that this actually works as well as it does, but you sort of point them in some specific direction, and now they act as if that is their goal, and they can, you know, even like we're no longer talking in, you know, philosophical hypotheticals, like this is all being done right now, right? They can do very creative things in pursuit of the goals that you give them, including even lying, you know, in pursuit of those goals, right? Like hacking their, you know, like we've seen examples of LLMs that are give it a task to get the highest possible score in such and such a game, and then they figure out that they can hack, you know, the machine that the game is running on in order to get the highest possible score. So they're doing the kinds of things that a highly motivated person might do in that circumstance, okay? Now, you know, you're asking, okay, but is that really its motivation? right? But it's like we don't even have to talk about motivation at that point. We could say, you know, when an AI says, you know, I'm happy, I'm sad, is it really happy? You know, if you had a robot that said, I taste the fresh, you know, I taste this nice strawberry, or I see this nice view out the window, does it really feel that, or is it just programmed to say it? Right? Okay, now the key point, this comes back to my answer from before, okay? We can ask the same question about you, right? Or rather, I could ask that question about you, and you could ask that question about me, right? I could say, well, you know, you are opening your mouth, you're making certain noises. You know, if I look inside of you with an fMRI, I'll see that neurons are firing to cause you to say certain things. But, you know, I have no idea if you really feel anything. Right? You have no idea if I really feel anything, right? This is the oldest problem in philosophy,
well,
maybe.
I have a pretty good idea that the machine doesn't feel anything because it doesn't have a body.
But why is that the thing that matters?
Because that's how humans feel things.
Well, I would say that, you know, mostly it's happening in the nervous system, right? And you know, you could say the machine does have a body. It's just that its body is made of silicon. It's, you know, I mean, we wouldn't want to say that, like, Steve, you know, if someone is very disabled, you know, if they lack the sensory modalities that we have, that means that they can't really feel things, right? But then the limit of that is, well, what if you removed all of our sensory modalities? It seems like I'd still feel things. I mean, in fact, if I'm arguing with someone over the internet, right, like, you know, neither of us see each other, neither of us, you know, smell or feel each other, right, but you know, we still clearly have emotions about it, right? And so now, if I swap out that person for an AI, right, and of course I don't even know when I'm sitting at my terminal that it's an AI, then why does that become different? I mean, this is the question, and, you know, I don't say that there's not an answer. I just say, you know, one needs a non-question begging answer to such questions, right? This was the point that Turing made 75 years ago.
I don't think it's an unanswerable question because the computer doesn't have a body. It cannot feel. It can predict. It might become very good at predicting.
Yeah. How do you know that?
Hold on. What a human would feel in similar circumstances because it's got lots of data to determine that. So it can
okay, so you would.
Then it can get feedback back and say, well, this is what I'm feeling.
So wait a minute. So even if it perfectly predicts everything that the human does, okay, you say it doesn't feel because it's made of. Okay, so what if I take the silicon chip that it's running on and I start replacing the silicon, you know, transistors one by one by biological cells, right? At what point does it start feeling?
That's my question.
Okay. All right. Well, you know, I think I don't think that anyone has ever identified a non-question begging criterion here, right? I think, yeah.
So, like, for example, you are like made up of a physics computer, and so like you could exist on a computer, and then by argument you wouldn't be feeling, but you wouldn't tell the difference between that right now.
I mean, there are people who believe that the entire world is running on a computer, but yeah. But yeah. I mean, these are the questions, right? Like, it doesn't seem like the crucial dividing line should be: is this running on a carbon substrate or a silicon substrate? Like, if you say it's important that we have a body, then what is important about having a body, right? Like, what are the crucial physical things? You know, how does having a body allow us to exploit the laws of physics to be conscious in a way that, you know, a silicon machine would not be able to, right? This is the thing that I demand the non-question begging answer to. I've never heard it.
Anesthesia?
What?
Like, you know, like all the systems neuroscience, like circuit level results that got Nobel Prizes, like grid cells, like plasticity and G1, they're all on anesthetized animals, and if you've ever had surgery, had anesthesia, you know you didn't feel anything. So that's like a good definition of like conscious experience, that it is that which is not anesthetized, and we don't even understand how it works.
Yeah, well, that might be an okay definition for like an organism that we've already agreed is conscious, right? And then we say, okay, well, consciousness is whatever it loses when we anesthetize it. But then that doesn't help us much with like the case of an AI or
circuit level, like the stuff that you would say is related to what CNNs do in the visual system, those things do not change with anesthesia. So to me, it's like something can compute things, and you wouldn't even notice the difference between when it's conscious and not, but you could know that it's not experiencing those things. I feel like experience is different from just the circuitry of our system.
Yeah, so look, it's possible that we would learn something from anesthesia about the neural basis of consciousness, and yet even if we learned everything that could be learned that way, there would remain the question, like, why is this not just the sort of executive control system? Like, why does it feel like anything to be there, right? That would still be kind of a philosophically unanswerable. Yeah? Oh, good.
The quantum computing in ML, it doesn't really seem super advanced or useful at the time. I mean, is my right in thinking that?
Yeah, so like 15 years ago, like the quantum computing companies realized that like the way to raise money was to say this is going to revolutionize machine learning. That was what people wanted to hear, right? So you know, they were happy, investors were happy, journalists were happy. The only problem was that none of it was true, right? right? And this narrative just become impossible to dislodge, right? I've been trying on my blog for 20 years, but it's like, you know, pushing a boulder up the mountain, like, you know, Sisyphus, like, you know, I can't really do anything. So you know, the truth is like it is possible that there will be quantum speed-ups for things that matter in machine learning and AI, but as far as we know today, those speed-ups seem to be quite modest. That's just what I was talking about before, right? We know how to get these Grover-type speed-ups, but it'll be quite a long time before Grover-type speed-ups will be a win in practice, because they need a fault-tolerant quantum computer in order to run. Fault-tolerant quantum computer, optimistically, might have an overhead of like 1 million compared to, you know, a classical computer. So then what you're saying is, if n is the number of possible solutions that I have, then I need n to be so large that it is much larger than like 1 million times square root of n, right? So when does that happen? Well, that eventually happens, but only when n is in the trillions, right? So Grover can give you, you know, advantages, but probably only for very large problem instances, and for most optimization and machine learning problems, that's kind of the best thing that we know, is Grover-type speedups. People have been trying for 20 years now to find better than Grover quantum advantages for machine learning. I strongly support people working on that. You know, even, you know, my own students work on such things. But sometimes, you know, discoveries have gone in both directions. So like we had a really great candidate for an exponential speed up for a practical machine learning problem, which was the Netflix problem, the problem of like recommending movies to, you know, or recommending products to a user under some, you know, idealized model of that. And you know, there was a quantum algorithm published in 2016 that got an exponential speed up for that, over the best known classical algorithm. And so now I had an undergrad in my class here named Ewin Tang, and I gave her a project to try to prove that this quantum speed up is for real, meaning rule out, you know, so it was not a question about the quantum algorithm. This is a question about classical. Right? Can you rule out a similarly efficient classical algorithm to do the same thing? And so she spent a year on this. She had, you know, several fallacious proofs, couldn't do it, and then at the end of the year, she said to me, look, I think I know why I haven't been able to rule out, you know, a fast classical algorithm. I think it's because it's not true. I think, you know, there is a similarly efficient classical algorithm, and I was skeptical, but she turns out to be right. And then building on what Ewin did, this is 2018, a whole bunch of the other quantum machine learning algorithms that were out there were then dequantized. So this was an amazing thing, and intellectually, it was not so great for the field of quantum machine learning, which I think has still not recovered from what my student did 7 years ago. But we continue to look for, you know, maybe there's an exponential quantum speed up for a machine learning problem that matters in practice. But if, you know, and which is not itself about quantum mechanics, you know, there, sure, you can get that. But, you know, exponential quantum speed up for a practical classical machine learning problem. But if so, I think we're still looking for the compelling example of that. Someone who hasn't had a chance yet to ask a question? Yeah.
So coming back to all of these computation problems,
yeah.
a common pattern seems to be that we're really testing the limits of space and time. Right.
You could think of it that way. I mean, look, you could say, you know, the whole insight of computational complexity theory, once it started in the 60s, right? So people developed this whole understanding of what is computable, what is not computable, you know, building on Alan Turing in the 1930s, right? And then in the 60s, people started building actual computers, and they realized that often what is computable is just not the relevant question at all, right? Because like most of what we want to do, we know that it's computable, right? The problem is merely that the natural way of computing it would take much longer than the age of the universe, right? And so now it becomes a question of resources, right? Of like, you know, your computer is embedded in space and time, and it only has a certain amount of them, right? It has a certain amount of, you know, we're very far from like getting to the fundamental limits of what the laws of physics would allow, right? No one actually builds a computer that does one step per Planck time, for example, right? Or that stores, you know, the other related bound is how many bits could you store in a given region? And the answer is about 10 to the 69 bits per square meter of surface area. Okay, this is the most that you can store in any region without that, you know, putting so much energy into that region that it collapses to a black hole. Okay.
What's that result called?
That's called the holographic entropy bound. Yeah. So yeah. Yeah, so we're many orders of magnitude away from, you know, saturating this limit or this limit, you know, like at least, dozens of orders of magnitude away. But, you know, if Moore's law were to continue for not that much longer, then we would have to get to those limits, right? Or stop. Yeah, sure.
How do we trust space and time?
How do we what?
How do we trust space and time?
Well, what do you mean by trust them?
Solving one of these problems in the dream.
Okay.
And we can just keep going. Maybe
Yeah.
And we can keep going there.
Yeah.
But then we wake up and realize all of it was set up.
Yeah, so
all of the time in the dream.
right. So yeah, so it's interesting. I mean, one of the standard ways to like tell whether you're in a dream or not, right, is just like to look at your watch and then look at it again, right? And just see like, am I seeing something stable here? Right? Usually when you're in the dream world, right, if you can have the presence of mind while you're in the dream to ask questions like, can I read this text and then read it a second time and see the same thing as I can tell you? Usually at that point, actually, if it's me, I would just wake up, right? But, you know, apparently there are these lucid dreamers who can ask such things while still staying within their dream. Okay, but usually, you know, this is a, you know, you could say like, you know, the standard definition, like reality is that which doesn't go away when you stop believing in it, right? Like, you know, you could say like the real physical world is, you know, is the thing that stores information, you know, external to us that we can't just change by effort of will, right?
Actually, I'd like to add something to what you
okay, yeah.
So when I was like really young,
okay.
I literally like couldn't tell the difference between when I was dreaming or being awake.
Really?
Right, so I literally couldn't tell the difference at all. And so that was very scary for a long time, and I had a lot of difficulty. But in order to literally make sense of the world so I could be a functioning human, I had to start to figure out like what is when I'm awake, what is when I'm sleeping, like, and there's like a certain logic to it.
But okay, well, how old were you? 3. Okay, and you remember this?
Bits and pieces.
I see. Okay, well, I mean, what's...
And then I got a lot better around 7, 8.
I see. No, I mean, what's interesting was that you knew enough to, you know, ask those questions at all without, you know, having the answers to them. Yeah. So I would say, look, usually like when someone hands you a computer, right? The permanence or reliability of the space-time manifold is not near the top of your concerns, right? Your bigger concern is what if this computer just doesn't work, right? Like what if someone built the computer wrong, right? It's buggy. It's it's this or that, right? So one thing we do is we test things, right? Another thing we do is we try to prove correctness of programs. Now, of course, any proof of correctness is only as good as the assumptions that it's based on, right? So like you have to assume something like about the reliability of the physical world, right? And in fact, even the computers that we use now, like a few times per year, a cosmic ray is going to pass through your microprocessor in your phone or your laptop or whatever, and it's going to cause an error. Right? Now, normally that just doesn't matter for us. If you're running a data center like Google or Amazon, then that actually does matter. Right? You actually have to think about physical errors, including cosmic ray ones. Okay, but yes, the building a precondition for being able to build computers is being able to build any kind of hardware that is reliable enough that it will do the same thing over and over, right? And if we didn't see that, that would, if all our attempts to do so, resulted in hardware that just did like Alice in Wonderland, completely different thing each time, then that might be a good sign that we're actually in a dream. Yeah.
Do you believe generative AI will get us to AGI?
That's a hard question because part of it depends on the definition of generative AI. Right? It's one of these things. It's like some people say that string theory must work as the great unified theory of physics of quantum gravity, and the reason for that is that whatever ends up working, it will be called string theory. Okay. Okay. So likewise with generative AI, right? It's like whatever ends up working, people may decide that it is part of this paradigm after all, right? But no, look, I think that the approach of training on massive data, has clearly had vastly, unbelievably more success than the sort of logic-based approaches that came before. This was, the biggest paradigm shift of the field, and there was a whole old guard that had invested decades in these older approaches that didn't work as well, and that had to face this enormous reckoning over that. Fortunately for me, I never had a dog in the fight, so I could just immediately say, okay, yes, this approach is working, where the other one wasn't. I think that if there is a fundamental barrier to, let's say, LLMs, trained at present, doing pretty much all the intellectual work that we do better than we do it, then I do not know what that barrier is. Okay, and that's the scary thing about the coming decade or decades. So, one way or the other, I think we're going to find out. Yeah.
If I could ask a very similar question, but a little bit more technical. Do you think autoregressive transformers are going to lead to AGI, or do you think we're going to have to figure out?
I don't know enough to say. I really don't know enough to say. Yeah, sorry. So maybe one or two more questions, then I don't want to keep everyone. Yeah. All right. Yeah, sure. Hey.
All right. What's your take on randomness coming from very simple rules and deterministic processes?
Well, I would say, a deterministic process by definition, if we also know that process, right, then in principle we can predict all the outputs of that process, and so they are not random. What they might be is pseudo-random, right? So they might be unpredictable to an adversary who has only a limited view. Right? And one of the great achievements of theoretical computer science in the 1980s, for example, was to formalize those concepts, right? And so, like Andy Yao, won the Turing Award, largely for, the modern definition of pseudo-randomness, which says that something is pseudo-random if no polynomial time algorithm can tell it apart from truly being random. Right? And so there are many, many simple deterministic processes that plausibly, as far as anyone generate sequences that are pseudo-random by that definition. So, for example, many cellular automata, Wolfram's, Rule 30 or Rule 110, right? Very plausibly, will generate cryptographically pseudo-random sequences, right? They're not unique in that respect. Many, many other things will do the same. Okay, but that all of that depends, on the assumption that P is not equal to NP, right? If P equals NP, then there is no pseudo-randomness in the Yao cryptographic sense. Okay, but even if P is not equal to NP, we don't know that it follows that pseudo-randomness exists. We know that it exists if and only if one-way functions exist. So functions that are easy to compute but hard to invert. Right, so a big theorem from the 1990s was that one-way functions exist if and only if pseudo-random generators exist. And once you have those things, then you can get started building like the whole rest of modern cryptography. Right? Now, or at least the symmetric key kind. Right? If you want public key encryption, then you seem to need something more structured. Like you don't get that from just a cellular automaton, as far as we know, right? To get public key encryption, like the kind of encryption that doesn't require a pre-shared secret, there you seem to need some special mathematical problem, like either factoring, discrete logarithms, something involving elliptic curves or lattices. Okay, and then this introduces a big trade-off, by the way, right? Because the more structure you have in your cryptographic problem, the more danger there is that someone is going to solve that problem. If not using a classical computer, then maybe using a quantum computer. Right? That's exactly what happened with Shor's algorithm, which broke much of the public key encryption that we know about. Not all of it. Right? But most of the public key encryption that's currently used. Okay, but if you just want pseudo-randomness, then that seems like a much more generic thing. Seems very, very plausible that we should have that, even in a world with quantum computers. Assuming, of course, that P is not equal to NP. All right, so maybe like just you, yeah, like one more.
Yeah, so back to LLMs.
Yeah, all right.
One big area of research is like model evaluation.
Yeah.
And so I was kind of imagining like how will computer scientists and cognitive scientists kind of collaborate on something like cognitive complexity analogous to computational complexity. So there's more of a spectrum of what intelligence is on a given task. You can have some sort of like classes of what an intelligent system is.
Yeah, so I don't know how to define cognitive complexity, right? Like, and then there is something I think really tricky here and really that really needs to be understood better. Like, it seems intuitively obvious that like some LLMs are smarter than other ones, right? And we can quantify that by saying, well, they get higher scores on these evaluation suites, right? They get a higher LSAT score. They get, and as you make in LLM smarter in some ways, it seems to also typically become smarter in other ways, right? And you see, you even see them going through much of the same progressions that like a human student would go through, right? Like I remember, like messing around with GPT-3 a few years ago, before ChatGPT, right? And it was struggling with basic arithmetic. So you could say like, and people could and did point to it and laugh and say, oh, look, it's like barely out of nursery school, right? But okay, we all know what happened, right? It's as you just keep scaling it up, it gets to junior high, it gets to high school, and now I would say it's in graduate school. Okay, right? It can, yes, I can design problems that my grad students will be able to solve and that, GPT-03 will not, but it won't be trivial. Right? I'll have to think to design such problems. And so there does seem to be some kind of notion of cognitive complexity, and yet it seems like not a very good match for any of the notions of complexity that we know how to formalize, like computational complexity, right? So like even, you know, like I can explain to, you know, I can easily explain to my 8-year-old, let's say, you know, the factoring problem, right? And then already, you know, I could say, you know, factor this 3,000 digit number. You know, he can't do it, but he understands what the question is, right? And, you know, and now we're already maybe beyond the ability of any known classical algorithm running within the lifetime of the universe, right? But, and yet we haven't budged on the cognitive complexity scale. Like we haven't, you know, made the type of problem more advanced at all. So maybe it's just something about like how much knowledge you know you need, how much, you know, like my worry is you know, it's not obvious to me a priori that there is a formal definition of this cognitive complexity at all, like separate from just like the history of human civilization, right? Like here is like something is more cognitively complex if you needed to know more of how things developed in our civilization in order to understand them, or something like that, right? Very hard to formalize that. I would love if someone could do it. All right, so I want to let people get home who want to go home, and I should also help put my kids to sleep.
So, let's first of all give it a shot.
Yeah. But, I mean, thank you for coming. Thank you for your questions. Thanks for, yeah, it was an honor to be here. Yeah.